All right, here we are, we're back. This is Big Idea 2. Within Big Idea 2, a lot of times we talk about a thing called molecular geometry. Some students seem to find this really confusing, difficult to keep track of, and I don't think it is. I think the problem is that it does require a bit of memorization. So just sort of set yourself to know that when it comes to this particular topic, if you don't have several things memorized, you're not going to be able to do it very well. All right, so this is all based off this idea called the VSEPR. Okay, my P has an extra extension. PR, so VSEPR. And this is valence cell electron pair repulsion. And essentially, all this model is saying is that all of molecular geometry, which is the shape that the atom or the bonded set of atoms, the compound, you know, whatever it is, it's going to make a shape, and that shape is going to be based off the electrons not wanting to be around each other. Right, because both of them being negative, they tend to repel each other, right? They don't want to have anything to do with each other, you know? They're just, ew, get away from me, you're negative. All right, so anyway, so they're just moving as far away from each other as possible. And then the other part of this is that when atoms are bonded, when they come together, let's say we have carbon dioxide, so we have carbon here, sharing a couple of bonds with some oxygens. When they come together, well, these electrons, these 4 electrons in the carbon, they were in their own orbitals, and then these 2 electrons were in another orbital here in the oxygen. So what happens now that they're in this bonded situation? Well, what happens is that there is now a hybrid here. Whatever the orbital was here and whatever the orbital was here, it's a hybrid. And actually the hybrid in this case is what we call an sp hybrid. So it's a hybridization between an s orbital and a p orbital, right? And so if an s orbital is spherical and a p orbital is like this, you know, they get together and essentially make a baby, and maybe it looks like okay, forget that, stupid. But anyways, you understand that when we say hybridization, we're taking 2 different things and making some kind of a mixture of the 2, right? All right, so let's get into this. And really, what I like to do is learn how to understand domains. Sorry about that. A domain is going to be 2 things, right? And this is the simplest way to think about it. So one is bonded atom. So a bonded atom, that's the first way to think of a domain. The second way is to think of an electron pair. All right, so in here, let's look at how many domains we have according to these rules. Well, you always take the perspective when you're looking at molecular geometry from the central atom, which we learned in the last video is going to be the least electronegative atom is going to often take the central position. Another way to check it out or to look at it is oftentimes the central atom is the one that's alone, whereas the ones around it, there's multiples of it. So here we have CO2, carbon in the middle, and the 2 oxygens on either side. So if we look at that carbon in the middle, it has 2 bonded atoms, right? Now you might say, well, hey, look, there's a double bond here and a double bond here. Doesn't that make it 4? You're not going to be concerned about how many bonds between the atoms, just that it is bonded to an atom. So when I look at how many atoms, carbon is bonded to 2 oxygen atoms. That gives us a total of 2 domains right here. And then if I look at carbon, it does not have any pairs, okay? So there's no electron pairs in carbon left over because it's using all of its 4 valence electrons for these bonds. So that means it has a total of 2 domains. And so domains are counted in this sort of way. You have your first domain is going to be S, and S only has 1 orbital, so then you move on. So if you have 2 domains, I'm going to go to P, okay? So if I had 3 domains, let's say that I had another sort of atom with 3 domains, and then I would go to sp, and P has 3 different orbitals, so this would be sp2, right? So I could get 3 different orbitals of P in order to hybridize. So I could go up to sp2, sp3, and then I'd have to move on to D. Before I get too far on this, I want to sort of capture some of the geometry here. So let's say I do have CO2 and it's a sp orbital hybridization. Well, what shape is that going to make? So when we look at the molecule right here, one of the reasons that I drew it this way is because when you think about this, so all the electrons are going to be here, around. It's going to have all these pairs of electrons around these oxygen atoms, right? And they're going to want to get away from each other as far as they possibly can. So they're going to assume this shape, and this shape we call linear. So if you have sp orbital hybridization, your shape is linear. Right, and so you could say that generically that would be any molecule that assumes this kind of shape. Now, if my center atom had a lone pair here, right, it would change from sp to sp2, right? And so what would that do? Well, lone pairs, they actually tend to push the electrons away further than electrons than just single atoms do. Now these atoms will have electrons around them and such, but if it's a lone pair, it's just pure electrons. So they tend to push more space away from them. So think about it that way, as these are more repulsive in that sense, and just slightly. So let's look at sp2. So if we have sp2, if we count our domains, if we look at our Lewis dot diagram, and that's really the best way to count your domains, is to draw your Lewis dot diagram. Refer to the last video or the Lewis dot diagram video for how to figure that out easily. So if we looked at sp2, there is maybe a couple of examples right here. Well, let's just draw it generically, but the one that comes to mind is boron tetrafluoride here, and so this one is kind of a different one in that it doesn't have a full octet, but it's okay with that. So it's one of those exceptions to the octet rule. So what we call this, we just call it an incomplete octet. So as you'll notice that boron can be stable here with 6 electrons around it instead of 8. So anyways, but if we take a look at this, if we look at boron right here and look at our rules, we have 3 bonded atoms, right, and no electron pairs. So that would give us S. There's 1, so we have 3, and then we have 2 P's. So sp2 is our orbital hybridization, and we have no bonded pair. So this would be the shape made by an sp2 with no bonded, with all bonded atoms and no electron pairs. So what shape would that be? So what's going to happen is, of course, these are going to go as far away from each other as they possibly can. And so it's going to assume this sort of triangle sort of position, right? And these are going to get as far away from each other as they possibly can, which if you take this complete circle and divide it up 3 ways, we're going to get 120 degrees in between each of these pairs. Of course, this one back here was going to be 180 because it's just flat. But we have 120 degrees in between each of these right here. And so anytime you have sp2 hybridization, and it's 3 bonded atoms without any lone pairs, this is what it's going to shape. This is the shape it's going to make. We call this shape trigonal planar. Okay? We call that shape trigonal planar. And some examples of that, BF3, SO3 would be one. The nitrate would have one. The nitrate ion, polyatomic ion. Let's see what else. Carbonate would fall under this category. And let's look at. So what if it didn't have just bonded atoms? What if it also had a lone pair? you know, so let's say, for example, like SO2. So when you look at sulfur dioxide, it's bonded to 2 oxygens, right? And it also has a lone pair right here, and one of these is a bubble. So it's 2, 4, 6, 8. So sulfur dioxide has an extra lone pair at the top. And see how I drew it like this, where these are pushed out to the side? Well, the reason for that is, like I said earlier, this lone pair of electrons is just pure electrons. So it's going to push these away further, actually, than this would have. And so actually I probably should have even drawn it more. But what we call this right here, if you have sp2 and one of them is a lone pair. So see, we have sulfur in the middle, has 2 bonded atoms and 1 lone pair. So that's a total of three domains, and so that gives us sp2. Same one we've been talking about this whole time. And so it's going to push this bond angle between these ones is going to be a little bit greater than 120. So if 120 is equal, remember this pushes these away even further. So we would say something like this. It's a little bit greater than 120. So the angle is actually, I did that wrong. So the angle is greater than 120 on either side. That's the case. And down here, the angle will be less than 120. All right, so that's kind of a way to think about that. And then remember, this being a trigonal planar, the shape of this is what we call bent. And so here's where a lot of this memorization comes into play. All right, let me go over a few more examples real quick. So we talked about 3. Well, what if we had 4 domains? So 4 domains is going to give us 4 spaces. So 4 domains, and that would be like a sp3, right? Because there's 3 p orbitals. So you have 1 s and 3 p orbitals. That gives you a total of 4. So you count 1 for the s and 3 p's. So, so what's going to happen with that? Well, that would be something like CH4, right? So CH4 has 4 domains, and if you look at CH4, it's got 4 bonded atoms, and so what's going to happen with its geometry is this is going to become, you know, exactly spaced apart as far as they possibly can, which if you divide it up by 4 would be somewhere around 109.5 degrees. Okay, so so all of these are going to be like that, and the shape of this, where it's all bonded atoms, is a tetrahedral. Some examples of that, you know, CH4 is one, the ammonium ion is one, let's see, this would be the perchlorate ion, let's see, sulfate, I believe, is in here, ion, or polyatomic ion, I should say, and the phosphate polyatomic ion. So all of these are the situation where we have just a central atom, and we're surrounded by other atoms, and there's no lone pairs within there. Now, if you end up with a situation where you have like NH3, so NH3 it's bonded to 3 hydrogens. So this is ammonia right here, and then it also has 1 lone pair here at the top. And so that's going to form a little bit different shape because this, remember, will repel these more. So this angle right here is going to be greater than 109.5. And then these ones are going to be less than 109.5. So you just you could take your 360, divide it by 4, and sort of predict that bond angle right there. And so the name for this, if you have 1 lone pair, is trigonal planar. And if you had 2 lone pairs, let's say that we had a situation where we had 2 lone pairs. Let's go ahead and get rid of this for a second. Let's see, water is like that. So, so we have oxygen and 2 hydrogens on there, and then the water still has two lone pairs up here. So this is 4. So we have 2 pairs, 1, 2, that's 2 domains, 2 bonded atoms, 3, 4. So we're still sp3 orbital hybridization. So that's what we say the hybridization of the orbitals has gone to. But this is going to make even different shape than this, because these lone pairs, like I said, push this even further away. And so the bond angles are going to be you know, even greater than this here, has a real specific bond angle. And this one is also called bent. So, but this is in the tetrahedral sort of basic shape, but this is called bent here as well. So we had a bent in the last one, and this is also a bent. Some other examples of this, well, water's kind of your best example of this. Water's pretty unique with that. All right, so let's go ahead and just keep going, because we have a couple more situations. Actually, beyond sp3, there's question as to whether or not the hybridization occurs, but anyways, we'll just learn it just because it's important for you guys to just have a knowledge of it. But let's say it has 5 domains. So what would happen with 5 domains? Well, you have 1s, 3 p's, right? So that's 4, and 1d, so sp3d. So when we look at sp3d, its basic shape is what we call trigonal pyramidal. Bipyramidal. And so an example of that is going to be like PCl5. So, you know, 1, oops, sorry, it's chlorine, 2, 3, 4, 5. And so you can see that it's bonded to 5 different atoms. There's no lone pairs here. So this is your basic trigonal pyramidal. So that's PCl5. There's other examples, maybe PF5, sorry. So I know that phosphorus can do this. So PF5, and let's say that you had a situation like SF4. So SF4 is bonded to 4, 1, 2, 3, 4. But it also has a lone pair here, which is going to push these angles even closer. This is called, they call this seesaw or folded square, I've heard. I usually see seesaw right here. But essentially, you probably only have to be able to identify at this point that it's this orbital hybridization. You might have to, on the test, be able to, if you don't understand what this is, I wrote the word seesaw very terribly. There's also, of course, a situation where instead of 1 bonded pair, you could have 2 bonded pairs. That would be like chlorine tetrafluoride. So chlorine tetrafluoride, you have chlorine there in the middle. You have 3 fluorines on that, and 2 bonded pairs. I mean, 2 pairs of electrons, 2 lone pairs. This one is called T-shaped. And then we have another one that ends up actually looking linear, where we have 2 bonded atoms and 3 lone pairs. And so, but all of these are sp3d. So remember that the shape will change depending on how many lone pairs versus bonded atoms there are. If it's just bonded atoms, it just does this equal spacing. When it gets to having lone pairs, it pushes it away even more. So the final one, let me go ahead and just throw this up here for you. The final one, of course, which you know, you're only going to get a few examples, like SF6 is a classic one. So sulfur can bond to 6 fluorines, right, and make an expanded octet. See, 1, 2, 3, 4, 5, 6. There we go. That is beautiful. All right, and so SF6 is going to have 6 bonded atoms. So with 6 domains, where are you going to go with orbital hybridization? We're going to go sp3d2. Now, like I said, the chemistry now tells us that this really doesn't occur. This orbital hybridization doesn't occur really probably past sp3. But at the same time, you may be asked questions and sort of expected to know this. SF6 is your classic example. I think it's probably the one that they're going to ask you. And so what is the shape of this? Well, it's actually called octahedral. All right. And beyond that, I don't think that you're going to need to know more. But if you end up with a lone pair in here, it becomes square bipyramidal, and if you end up with 2 lone pairs, it becomes square planar. So one thing that is kind of good to have is this. Something like this would be helpful for you to memorize it. So here we have, it's kind of a little bit of a recap. We have our SP hybridization, so that was only 2 domains, and that was linear. And then we went up to 3 domains, so we got our trigonal planar, but we also could have a lone pair in there, so we ended up with our bent, right? This is just recap. And remember, our bond angles here were 180, we went down to 120, and then with our 4 domains, we're at sp3 orbital hybridization. It's a tetrahedral shape. It's good for you just to essentially memorize the basic shapes to begin with. And sort of get an idea of where these sort of extra shapes fit in. So, so if we throw a lone pair on there, now it's trigonal pyramidal, and then like water we talked about was also bent. And so when we go to 5 domains, our angle will change from, we have actually 3 of them at, let's see, 2 of them at 90 and the other 3 at 120. So you have essentially a linear with a trigonal planar around the inside of it, you see. So essentially if you took these 2 and like bred them, you would get this. And so until you start adding lone pairs, that pushes more stuff away, and that's where you get your seesaw and your T-shaped and then your linear right here. And then we went down finally to octahedral, which was our SP3D2. I'm not quite sure why they wrote the D first here. I suppose that's okay. That was where we got these kind of, I didn't really go over these ones right here, but anyways, that's a rundown of molecular geometry. Like I said, a lot of memorization, and there will be some questions on the AP exam covering this. So hope that helps and gives you a good idea of how to do that.